when you
Recording in
add the
progress.
direction into it, that's when you have a vector. So this should be hopefully pretty straightforward, but again, we have vector or scalar. And A is telling us, so let's see, flight trajectory is north-northeast. Okay, that sounds weird, but I guess it's, north-northeast. So you're going north and then a little bit east, I don't know. And so this is a direction. And then for 1,200 miles, this is a magnitude. And it's kind of the same thing as a distance, right? Or that's how I think of it. But we're using these kind of more proper direction magnitude terms. So this one has to be a vector, right? Because it gives both. Part B is 1,200 miles. So this is just distance. So just distance means it's just representing a scalar. Oh, I should have written that in blue. That's okay. Part C is saying speed is 540 miles per hour. Again, that is just so distance isn't the only way you can represent magnitude. Magnitude really just means number. So magnitude is like a number, right? Because a direction is not a number. A direction is north, south, east, west, and everything in between, right? And north, northeast, and all these weird things. But it's what way, or maybe you say you're going 90 degrees this way, or something like that. Left or right is even a direction, but technically we would use maybe east or west or something. So this one is also going to be a scalar because it is just a number, although it's speed. Just majority of the time up until today, we referred to like magnitude. Typically, we just used distance because that we were measuring things and we were trying to find how tall is the building and how far away are you? How far out is the kite? We were looking at distances, and now we're kind of incorporating speed. And I think, and velocity, right? But also, I think it was Michael that asked this about the bearing. I forget if it's today or tomorrow, or Thursday, but this week we are going back to bearings. So even though it was skipped, like in whatever section before, it is in this section. And so maybe that's why it was skipped, because we were just going to do it later. And maybe it's repeated in the textbook. I'm not entirely sure. So this one we have north, northeast, again, the direction. And then 540 miles per hour, this is the magnitude, right? So this here is going to be a vector. Okay. So now we think about vector equality. So like up above, we talked about this. We said these two vectors are actually equal because we can see they're in the same direction. They don't start at the same point, but they start at a point where they move then in the same direction and the same distance. Granted, I don't know if that's like 100% true that LA to Helena and Austin to Chicago is the same distance, but I'm betting it's pretty similar because they are using that as an example, right? So if we want vector equality and we want to see like how can we make two vectors that are equal or find out if these two vectors are equal or not, what we have is these examples here. So we've got, it says draw each pair of vectors and determine if they're equal. So we're going to have a little way to draw these and then say, are these the same? Yes or no? Because if I just look at the points, I'd say I have no idea. But if I figure out where they're pointing and the direction they're going in and kind of how many units maybe they are about, then we can determine, are they the same or not? And typically they'll try to not to trick you, but typically they'll try to make the vectors the same length, but they'll change the direction. So you might think, oh, they're the same length, they're the same. But if one arrow is going one way and the other is going another, this is what you'll see, right? So let's first start with V and W. So V goes from -3,1 to 1,4. So, okay, I'm going to label these by 2, 3. I think that's fine. So -3,1 would be here to 1,4 would be here. Okay, so this is V, right? And see how they bolded it. And maybe that's actually just what I was trying to do up here is bold, like bold my V. But yeah, in the textbook and in your homework and stuff, you'll see like these are just bolded and that means vector. Okay. So we'll write it with an arrow on top just to be very clear. But yeah, that's what that means. So there's my first one. Now let's get my second one. So I have 0, -3 to 4, 0. So 0, 1, 2, 3, 2, 4, 0. And this, what do we call this? W. Now you can see that, if I count, like to go from one point to the other, almost like if I'm counting slope, like rise over run, I can go, this goes over 1, 2, 3, 4 to the right, and 1, 2, 3, 4 up, I guess, right? And this one, does it do the same? 1, 2, 3, 4, and 1, 2, or maybe it's only 3, 2, 3. Yeah, okay, it was 3 up. It was 4 to the right and 3 up. So they both do that, which makes me think, okay, these could be really similar. That could be good. And another way that you could look at this is, or there's a few different ways, right? The arrows are also pointing in the same direction. And if we wanted it to look like right now, it looks like, okay, these should be the same, but we could also shift. If you wanted them to be directly above each other, they should be parallel, right? They should be parallel or be able to be shifted and placed on top of each other so that they're the same. And so if we were to do that, let's see. If we were to do that, we could shift this over to be above, we could shift the first point over 1, 2, 3 to the right, then shift this 3 to the right to be above that. And if we did this, let's just see what we would get. We'd get, here, right? And if I did this, then I could see this is like V. Okay, this is not exactly equal to V, but this is like V. And I could actually slot, if you could take your pencil, which, okay, maybe I'll use like a highlighter. Let's try. So maybe if you take your pencil and if you could take this line, so pretend my pencil's over this line, and then I'm dragging it up, and then I have it over this line, right? So if these could be, and I don't need to pick up my pencil, these are going to be the same vector, right? Because they're the same distance, which we counted out. They're in the same direction. So both of their arrows, if we look at their arrows, they're both facing this way. So this one's going to be a yes. Same direction, same magnitude, right? Now for part B, let's see what they gave us here. So in part B, I'll draw the first one, -4, -2 to -1, 4. -1, 2, 3, 4. -4, -2 is here to -1, -4. 2. Okay, here. Okay, so my direction is different than the first ones, but that's okay because these are a different problem, right? And this is vector A. And then I have vector B. Okay, so vector B, I'll do this maybe in red. So 4, 2 to 1, 4. Okay, maybe this is 1, 2, 3, 4, 2 here to 1. Oops. 4. Oh, okay, so 1, 4. They do overlap. I think over that. So make sure your arrow is at maybe that wasn't very good. Make sure your arrow is at the second point, right? Okay, so it looks like I could take my pencil or pen, right? Move from here and just keep sliding it over and get to here, which they look to be the same magnitude, which is great. However, right off the bat, when I didn't label, this is part of B. Right off the bat, I can see that the directions are different. So this is just automatically going to be a no. Because these are opposite directions. But they are the same magnitude. And I can see that. I mean, you could count it as well, right? So I could count this goes down to left or right, 1, 2, 3. This goes down to right, 3. So they're the same like distance, but I can see pretty clearly that their directions are different. So I don't even have to think about it anymore. Now we have, so these are how to look at vectors, how to read them or how to plot them, and how to figure out what direction they're in or what, where they're pointing, which we'll probably talk more about the actual direction because we didn't say like northeast, northwest, or whatever, right? Oh wait, number 3 said draw, oops, my bad. Draw 3, so number 3 said draw V in standard position. Okay, I completely forgot. I almost forgot to do this. So standard position means, and I kind of want to start over, but I should have like copied this chart because I don't really want to erase anything, but here, maybe we did. I need to show you what standard position is. I'm trying to, or maybe I'll write. I'm trying to erase some stuff without erasing everything. So let's put this back, B, and I'll keep also. Okay, so standard position, if that's what we want, what that means for V. So V is here. Standard position means the starting point is at the origin. So it's at 0, 0. So basically, no matter where you're, like we could take A, B, D, or W, no matter where they are, we can just literally, like, again, pretend it's like your pencil. And we aren't changing the size or anything. And we are just shifting it to wherever the origin is. If it's right, if it's left, if it's up, if it's down, it doesn't matter. We're just going to shift it. So we're going to take this V, and maybe I'll do it in dark blue like this to be sort of. So we're going to take V, and we're basically shifting this. We want the starting point at the origin. So we just figure out, okay, where do we shift that first point? And then we say, okay, wherever that shifted, the terminal point has to move the exact same way. So I went 1, 2, 3 to the right and 1 down. So this terminal point that we had here is going to go 1, 2, 3 to the right and 1 down. And then I'm going to connect the dots there and draw my arrow. And this is V standard position. Okay, so it just means starting is at 0, 0. Okay, so hopefully that's clear. So that's how to draw vectors, how to see if they're equal, how to change it to standard position. Sometimes if you really have no idea what's going on, you can change all your vectors to standard position, and then you can see like what the differences are in lengths, in direction, anything like that, right? Okay. Now looking at this next thing, vector arithmetic. So we can actually take multiple vectors and add them together. Like for example, say looking at this beginning piece, say I wanted to actually fly to somewhere in Maine, right? Say I wanted to fly up there. Well, maybe from Austin, there's no direct flight there. Maybe, I mean, okay. Or maybe say you're saving money and you're not flying directly there, right? So maybe you're flying from Austin to Chicago to Maine. So what would happen is you would have one vector here, right? But then a second vector there. And you could, like, you're basically, the two flights are two different vectors, and granted, your flight probably doesn't go straight, right? I'm sure our flights, the actual path is like, I don't know, right? But if it was a direct path, this is what you would have. So we'd have these two straight paths, and we can actually add these vectors together and even get like they form a triangle as well, right? So we can even get that distance. And what would it be if we were to combine the vectors and maybe, get the shortest path to the end instead of both, like something like this. This is the idea. And so let's take a look at this picture. So this looks like kayaking or whitewater rafting. It brings back bad memories of whitewater rafting when I was younger. But you have good experiences and you have rough experiences, right? Now, granted, everything was fine. I just get nauseous and seasick. So my instructor didn't speak English and he didn't understand. So he just spun our raft more and more. And then I threw up. So I think he got it after that and he felt pretty bad. But yeah, good times, right? Okay. So looking at this, you can see that this boat, we'll call this like boat number 1 and boat number 2, right? We can see that boat number 1, if you look like at the center and you kind of look at it's like pretending it's a graph, and look at its x-axis maybe a little bit, we can see that what direction it's kind of going in, right? And let's say, so based on the current, like what these, I think what these blue lines, like these light blue lines are, maybe these are currents. So what's happening is the boat is pointing in the direction of the line that I just drew, but the current might be pushing it in, in this direction. Like that might be the current is kind of moving you. And so if that's true, like something like this, then what's actually happening is we can add these vectors to get where is this boat actually going to end up. And I mean, I'm really just making this up from the picture, but there is a precise way to do it, but we're just trying to get the idea. So these two vectors might add up and they might say, oh, this boat is actually going right here and it's going to end up right in the rocks here, right? Whereas, okay, the next boat, it looks a little bit wonky maybe because it's like facing up, it's like facing the wrong direction, so it looks. But the current, so it's facing kind of north-south instead of more east-west, but the current, right, this like light blue line, it might be drawing it, and I'm drawing from the center of the boat, I should have done that with the black line as well, but so the current might be pulling it this way, right? Possibly. And so if we add the red and the blue vectors together here, we might get something like, going more in this direction. Like the blue is pulling the red and it might start turning and then, going down here and avoiding the rocks. So, and I mean, okay, maybe I'm explaining this not so great, but it looks like number 2 is better positioned to avoid the rocks. So it looks like. And vector addition is not, I mean, it's maybe a little intuitive, but sometimes it's not, because based on the magnitude and the direction, when you add these together, if the magnitude is stronger in one way or higher, like, because magnitude could be speed, right? So if the speed of the current is, I don't know, like 5 miles per hour or something, right? But the speed of your boat is 1 mile per hour, well, the current is pulling the boat way more. So it's gonna, so you're not gonna have a perfect line in between the two, right? So you're actually gonna be pulled more, which is kind of what I drew here, right? I'm assuming maybe we're not paddling very quickly, right? And so this line here, the blue is affecting us more than the red, right? And so we're being, maybe because the red is, maybe we're floating, and the current, we're just waiting and seeing, all right, what's going to happen with the current, right? So that's what's going on here. And really, how you can do this is you can also draw a picture that is a little nicer than what I drew. So maybe also, because what you technically should be able to do is then connect these, which I didn't do a good job, because like you're supposed to be able to connect your V plus W vectors So really it would be something like maybe that connects here, but okay. Maybe my picture is not drawn to scale or accurate, but we hopefully are getting the idea. So now if we're looking at adding vectors, what we see here is this, maybe I'm given vector V, right? I'm given vector W, and V is going in this direction, W goes here. And V plus W, so if I want to add these, it's going to be from the starting point, if you're starting with V, to the ending point of W. And that will be, if we draw this, right? I was showing maybe what the current, like how the vectors were shifted above. I wasn't really thinking of adding them, but if they're connected, then we can draw. So like in this first case, they were kind of more connected. So we could maybe then connect with this red line here, just like this first example. However, in the second case, you can see that our initial vectors, the red and the blue, they were going in completely different directions. Like they're not like from the same point here. They're not really connecting from the next point. And so if we have something like this, where my V is going in this direction, but my W starts at the same place in this direction, then to add them, it's somewhere in the middle, and one of them maybe has a greater pull than the other, right? But when we draw it, we would just draw it where V plus W is maybe something in the middle. And then we have subtracting vectors. So if we subtract vectors, so again, they start with a pair that's connected. So if I have V, then W, basically minus a vector just means the same vector in the opposite direction. So looking at W, it's going this way. We would just reflect it about this point, exactly 180 degrees, and draw it at the same magnitude in the other direction. So my W just changed there. And then you kind of think of it as adding maybe. But another way to see it too is that this V plus W, if I think of what we had before in blue, well, V minus W is again also just reflected the same way that W is reflected when we do minus W. So you could also, so you have two options here. You could reflect the W first and then connect them, right, and get V minus W, or you can keep them, get V plus W, but then reflect that across V, like reflect that across your initial vector there. And that will give you, okay. Okay, that will give you the V minus W in this direction. Okay. And then the second way, if you have vectors V and W that are starting at the same point, what happens is instead of, when we subtract, instead of coming out from that same point like we did to add, we actually just connect these two and make our triangle and say, what is the difference here, V minus W? And when we subtract this, we notice how if it's V minus W, our starting point is at the end of W, and then we go up to V, right? But if it was W minus V, the arrow would just be reversed, okay? And they said it here, difference of vectors, it's the same thing as saying V plus negative W. So even for this second one, you could probably do negative W this way, and then you'd get some type of addition. Okay, like maybe it would be here, but notice how those vectors are the same, the two red that I've drawn, right? So this is like V plus negative W, right? And this guy here is like negative W, right? So either way, you'd get something. Okay, so we want to sketch the following vectors. All right, so we have u plus v. So these are not starting at the same point. So we'll have to see kind of, what we do with that, because they're not starting at the same point and they're not connected. Like we need it to be either coming from the same point like this, or, connected like that, right? And maybe I should. So yeah, so we either need them connected, or like we saw before, one follows the other. So what we have to do when we want to add or subtract vectors that are totally like in random places, we just have to shift. Remember when we looked at them up here and we were trying to set them equal, we can shift anything to standard position. We can shift it. We could take these two vectors. Initially, these were the same, right? But they're just shifted in a different position. So we can shift them around so that they look like one of our, something here, and then we can add them together or subtract. So, okay, if we want to start with this first one and sketch this, we want u plus v. So what I would do is first, I would maybe, okay, you have an option here. You can either shift v so that it is touching at the end of u. So I'm going to say, here. So I can take, so I can take these points and I can just shift it. So 1, 2, 3, 4, 4 down and 1 left. 1, 2, 3, 4 down left. And redraw it. Okay, drawing skills are not great, but those two blue lines should be parallel. So you can also draw it like this, and then I have u and I have v, and then I can figure out, okay, to add these together, these are connected. So to add these together, I would create this, a point from the beginning of u and the end of v, and this would be u plus v. Right? Or I would have, I could also have them start at the same place. So I could take V and go up 1, 2, 3, 4, and then left 1, 2, 3, 4. Okay, up 4 and left 4. So then I take the end. Where's that here? 1, 2, 3, 4. 1, 2, 3, 4. Okay. Hopefully I'm doing this right, but I would go up 4 and left 4, and I would draw, this is also V, right? These are all the same V's, but now I could see that, so what I did is fine, right? What I did is good, but notice U plus V, it doesn't change for either one. It's actually the same. Oh, somebody asked a question. Okay, so David asked, why do they add like this and not just by adding them as a special property? So vectors, because it's a direction and a magnitude, we can't just say, oh, it's 100 feet plus 100 feet. Because it might be, 100 feet north with, but the spectral ones can. Spectral vectors. So I don't know exactly maybe what you're talking about. Is that what you're saying? The S one. No, sacral. The other one. Oh, scalar. Sorry. Oh, okay. I'm like, what is going on? Okay, so no, yeah. So exactly what. So Joseph, thank you, scalar. But David, yes, what you just said. The reason we can just add or subtract scalars is because they are just numbers. They are strictly just numbers. So if I say, oh, you're going 100 miles per hour, and then you go 50 miles, or I don't know, you walk 100 feet and then you walk 50 more feet. These are just numbers and we're giving no direction. So if it's like, how many total feet did you walk? Well, it's 100 plus 50, right? That's it. But if I say, I'm going to walk 100 feet north, but then, then, you know, I don't know, then 12 feet southwest or something, like you're going in different directions, and you can't just say, oh, if you're including the direction in your answer. So if you want your answer to be a vector, you cannot just add the numbers. Yeah, and Joseph is right. You can think of a scalar like scale that's measuring numbers. Let me turn on the light because it's going to start getting dark. Except I don't even know if this barely. Okay, so we're just gonna, it's gonna be dark, which is fine. Okay, so yeah, hopefully that answered your question. Oh, I can turn the brightness up too. And maybe with some more examples that'll help. So let's see. So like I said, we could choose to move V and B, let's see, we could choose to move V and have V be, you know, at the starting point of view, or we can shift V down and over so that it's at the ending point of view, and then we add it together. Either way, the vector you end up with is this middle vector, because notice how it's in between U and V here, which is exactly, you know, or, oh, that's the wrong example, but it's exactly how this example is, right? And then it's creates a triangle for the other one, which is exactly this example, right? So we have kind of either way, you're correct. And we actually don't have to do anything else here. We can just label and say, I mean, I've already labeled it, but this is U plus V. And then they gave us a similar picture and they said V minus U. So again, if you want V minus U, you either want to move U to be at the start of V or at the end of V. So it doesn't really matter where you go with it here, but like, let's say I took U and I shifted it. Let's do it. I shifted U to start at the same point as V. So that means I would shift it down 1, 2, 3, 8, maybe down 8 and over like 3, 1, 2, yeah, down 8 over 3. So then we have to take this point and also go down 8 and over 3. So something like this. I think that's where it should be. Okay. So if this is U, right, and we want to subtract it, well, we know that adding it would be adding V plus U would be here, connecting. So remember, adding, we would start at the end point. If it looks like this, adding V plus U, we start at the end point of, I guess in this case, maybe it doesn't matter, but this would be V plus U. The black line there. But if we want minus, we have a few options. We could take the reflection of U. So this is, okay, 7, 1, 2, 3, 3. So it could be 1, 2, 3 up and 3 over. I think here, okay, so my line is perfect. I think it would be like here. So this here, this line would be negative U, right? Because it's just going in the opposite direction. And if you wanted this to, if you wanted to subtract this, so to combine these, you can also say, okay, instead of starting from the same point, I can then shift the minus U so that it starts where V ends. And let's see, it just goes to, it would be this. So I literally just shifted, this is negative U. And so to add these together, I would again start here to here. Okay, my lines should, so in these two lines should be parallel because they're the same vector. So you could have either, oh, and maybe I wrote this wrong. Okay, so this is actually v minus u, and it's because I went in the opposite direction. So typically, and maybe I said this wrong, typically if we were adding, we would start at wherever v started, right? If we're adding, so let's see. If we're adding these vectors, we start where v started and we end where w ends. But in this case, I was starting where, if I start where u ends and end where we started, because I think that's the opposite of what I said. This sounds weird, but then this should be also be v minus u, sorry. V minus. I think it's a little bit easier to me, at least personally, v minus u. It's a little bit easier to take the vector and put it to the end of the other one. So we wanted v then u. And so I do think it's a little bit easier to leave v alone. And then wherever u is, get the start of u to be at the end of v, and then flip it or get the negative if that's what you need, or keep the positive, and then find your, because I like to connect it in a triangle. I like to always add that way, but subtracting can be a little bit strange. And yeah, hopefully David, oh, that was a while ago, but you said you see. So hopefully that made sense, whatever everybody was saying. So then we also have something, so the addition, this is kind of like fractions, where like addition and subtraction of fractions to me is harder than multiplication of fractions, right? And addition and subtraction of vectors is harder, I think, than multiplication of vectors. So now we look at scalar multiplication, right? And again, scalar just means number. So there's nothing fancy that has to be done here. If I want negative 2v and 3w in standard position, what that means is we get the distances. So let's start with v. So starting point, ending point. It goes down. So we go 1, 2, 3 down, and we go left 2, right? That's how I would get the distance of my vector v. And I want negative 2 times that. So first, what that means is you can just get 2, you can double this. You want this side to have 6 and this side to have 4. And we also want it in the opposite direction. So we basically want it going this way, right? And then we want it in standard position, meaning starting at 0, 0. So this starting point where we want it, which was the original starting point, we want to shift that to the origin, and then we want it to be 4 units to the right and 6 units up. Okay, so I started at the origin and I say I want 4 units to the right, 3, 4, 5, and 6 units up, and I'll draw my point there. And the arrow I want in this direction. I want it in the opposite direction. So I'm just going to draw it. Okay, that's like a curve, so that's not even straight, but it's okay. So I'm going to draw it like this, and this is negative 2 times v, right? So what happened here, like what did we do? We reversed the direction of v, and we doubled in length. And then for, what did we ask here? 3w. So now 3w. W is just, they started us off, it's 2 to the right and 2 up. So we basically just want this, we triple everything. right? And we're keeping the same direction. So the arrow is still this way. So we're moving our starting point to 0, 0. And we want, we triple it. So we want, 6 and 6. So 6 and 6. We want it out here. So let me draw one line. And this is 3W. And so all that this did was triple the length. This tripled the length. No change in direction. And then this little V over here is just drawn to show you or to explain. So V is a trajectory or a path. And basically just what's happening here is exactly kind of what you imagine. Like if I wanted, say I wanted half of that path, this would be like a half times V, right? We could do that if we wanted. If we wanted to cut the distance shorter, you can also make it negative. That reverses the direction, right? And then the last thing, let's see. This one. So the last thing would be if I wanted to double it. So, okay, say maybe it would look something like this. So you can also double it. So this goes twice as far as V, but same direction. And technically, like when I was drawing the negatives of these, right? Typically I would draw it, I would put a point here and then keep the same distance, and this would be like negative V. But if it's asked to be done in standard position, notice how like initially looking at V and negative 2V, it looks like weird because nothing, we didn't flip-flop it, but we do move where the arrow is. So you can always draw something in standard position, but the arrow, it's important on which side that's at. Okay. So now we have this form, I guess, that vectors in component form. So before, the vectors were either drawn or it was like, oh, -3, 1, 2, 4, 1. Like it was saying this point to that point. But you can also draw them in component form where we have these little brackets in A, comma, B. And this is, notice how vector notation is not the same as points notation. This does not mean A, comma, B like the ordered pair. Vector notation is actually, so if we were given something like this, looking at this example, if we were given vector V going in that direction, and there's the point Q here, the point P there, vector V, right? And then we have like some distance here and some distance there. The vector is PQ. You can write it like this. And the component form that's in this form, like this like weird, I actually don't even know what it's called, but some type of bracket and then AB, right? It is written like this, or this is what it represents. So it does not, like AB, this represents like X1, comma Y1, right? That's like an ordered pair. But this here, A is actually equal to some number X2 minus X1, where these are your points, your start point and your end point. So, and B equals Y2 minus Y1, where the starting point is X1, Y1, and the terminal point is X2, Y2, right? So just like we labeled at the beginning, that's what we're seeing here. So number 6 says, given this vector W with initial point 12, -10, and terminal point -2010, find the component form. Okay, so we can label these x1, y1, x2, y2, and then we can find it. And here, order totally matters, right? Because we have a start and an end point. This is like the arrow, the direction, it matters. So if I want to find the component for W, I would say, okay, this is going to be x2 minus x7, so -20 minus 12, okay? Then comma, y2 minus y1, so 10 minus, -10, right? So I get, what is that, -32 in the first component, and then +20. Okay, and maybe I'm writing. I'm not great at writing these brackets, but I'll do my best. And so from this, we can see that this is the x component. This is the y component of the vector. So it does not mean the ordered pair, not the same thing, right? And this is not an ordered pair. Just to remind you, this is a vector. Okay, so part B is now asking, let's see, what are they saying here? Part B is asking if W is placed with initial point 5,3, what is the terminal point of W? Okay, what this means is that we move the initial point 12, -10. Okay, so we move the initial point 12, -10 to be at 5,3. When we don't see physically the graph, it's hard to like count that, but there is a way that we can just solve this. So what we have to do is we just add the x and y components of W. Okay, so here we're going to take negative, we take the vector, so the vector that we got here, and we add the x and y components to the vector, okay? So we don't add it to the initial starting point, because on a graph, that's how I normally do it. I move, oh, I'm going 5 up, 3 right, or whatever, but we're not on a graph anymore. So we need to look at our component wise, like the actual vector. And so what we're going to say is it's going to be -32 is the x component, and we add 5 because this is the x component here, and this is the y of the new point. So -32 plus 5, and then we have 20 plus 3. Okay. Now this is going to equal the terminal point of W. So keep in mind, we are not going to be equal to we are not equal to a vector now. We are calculating for a terminal point. So basically, just like we discussed that every vector can start at the origin, that's kind of what we're pretending. And when we solve for this vector here, the reason we can just add 5, 3, even though it's not technically related to the 12, -10, is because we aren't using the 12, -10 anymore. We've already used both of these to get this vector, and we can just pretend this vector is anywhere. We could pretend it started at 0, 0. So if we do that, if we pretend it started at 0, 0, that's why we are able to just add, over here, but that's why we're able to just add 5, 3 into our components. So now the answer here, what do we get? -27, 23. This is the terminal point. Terminal point of W. And it is not a vector.
But you have the same vector as before, right?
Wait,
Like-
sorry, say that again?
I'm just, so if you have a new start point and then,
Oh, yes.
and a new terminal point, but you have the same vector.
Yeah, yep. So now we have, exactly. So we have a new start point at 5, 3, and the end point would be negative 27, 23. But if we were to calculate this vector again, it would be the same one.
It'd be the same. That's
Yep.
good.
Yeah, good question. So hopefully, this is kind of what we're looking at. You'll get more used to it probably once you do some homework problems with it. And then number 7 here is performing operations. So I do think this isn't so bad, because this is, it maybe is a little different than your standard operations on different things. But it is just multiplying and or adding different components, right? So let's see what this looks like. So they give us R and they give us S. Negative 4S, this is going to equal negative 4 times, I'm going to write S, 2, 3. Remember, this is not an ordered pair, but we kind of write it that way. And we're even going to kind of write our answer. Like it looks similar, but what it represents is a little different. So when we do this, just scalar multiplication, we just scale both components. So this is a lot like just kind of like if you just have parentheses, we distribute the negative 4 in. So this equals negative 4 times 2, comma, negative 4 times 3, right? Which is just equal to that negative 8 and negative 12. Right. So that's all we have to do there. Then this next one is a little different because we're scaling, but then we're adding 2 vectors together. So let's see like what that looks like, right? So we're going to just write 3 times R, which is 1, negative 4, plus 2 times S, which is 2, 3. So we can scale this. We know how to do that. So we know from the previous one that 3 can just be multiplied to these, 2 can just be multiplied to those. So let's do that first, and then we can add. So we'll get, what is that? 3, negative 12, plus 4 and 6, right? So from here, we just, and I'll write it equals. From here, we just add the X and Y components. So we are ignoring, like we are keeping the X and Y components very separate. So you add the X's and you add the Y's. So here, this is going to be 3 plus 4. So we're adding the X's, so like X and X. Then we have the Y's, Y and Y. So I get negative 12 plus 6. And this is going to come out to be 7, negative 6. And our answer is still a vector, but that's our new kind of, new vector after we perform these operations.
So can I ask you a question real quick?
Yeah.
So when you're given just this component form, like R is equal to 1, comma, negative 4, does that start, is the starting point of that the origin?
Okay. So if you wanted to draw it, the only way you could, if you wanted to draw this vector that they gave, right?
Yes.
The best way to do it is to start at the origin and then just move. You can move from there. Okay. However, you could start at any point you wanted, as long as you shift 1 in the X component and down 4 in the Y component. Does that make sense?
Yeah. So you could do it in like the standard position, but any
point works.
The
nice thing about these vectors, right? The nice thing about this component form is that your starting point can be anywhere, right? And typically, yeah, the origin is like the best place to start. It's just like the clearest and we all love it and recognize it, right? But you could pick any point your heart desired, right? And as long as you are moving in the right directions and ways and scale, you're
Yes.
good to go. Yeah. So that's a good question. Yep.
Awesome. Thanks.
Yeah. Okay, so now it gets a little bit weird in terms of notation or how we write these things. So looking at the next page, you see vectors in terms of I and J. Okay, so we love, love, love X and Y. X and Y, X and Y, our whole life, X and Y. Maybe A and B for an ordered pair or something. But now vectors, for whatever reason, love I and J. We have I represents always the X, kind of typically the X component, and J is going to represent the Y. And but we write it in this way. It's very, well, to me, it's very bizarre, but maybe it will make all the sense in the world to you, and that will be great, right? But let's just follow me, bear with me, and we'll see how we do this. So the unit vectors are vectors that have magnitude 1. So what this means, what is magnitude 1? Okay, let's see. If I'm given a vector, AB, okay, a unit vector, which we're calling U sub V. So U equals unit vector, or U, okay, I don't want this over here, is unit vector. And whenever you have a subscript, that means that that's the unit vector, like you're taking a unit vector of V, right, in that direction. So if we want U sub V in the direction of V, we are going to calculate it based on this equation. U sub V is the vector V divided by this, which I call the norm, but this is actually just the magnitude. It's how you write the magnitude of a vector V, and magnitude is the same thing as length. So when I was saying, you know, like, oh, we move 1 unit down and 2 to the right, like, so that has to do with that. And we'll see how we calculate that. It's actually kind of using, I guess, Pythagorean theorem a little, but you'll see. So like in number 8, if we want to find U sub W, and W is negative 815, well, what we can do is, so W, if I started at 0, 0, technically, right, for W, negative 8 would be to the left, 15 would be up. So it would be like something in this direction, right? Something like this, that would be W. So, and I know that it would go negative 8 this way, and it would go 15 that way, right? So look at me forming this right triangle. Oh boy. This is not related. We're not doing right triangle trig or anything. I mean, okay, it is a little related, but the way that we do this, and the nice thing, I guess, about this, if we want W, the length or the magnitude, and this is what we are given, right? Then we say magnitude squared, because that's the hypotenuse, is equal to 8 squared plus 15 squared. So here's where we are using the Pythagorean theorem. They just typically don't say it. They're just like, oh, we know this equation, but half the time you're like, why? But this is the Pythagorean theorem. If you don't see the picture, it makes very little sense, right? And so I'll get the magnitude of W squared is equal to, what is that, 64 plus 225, I think, so it's 289. And they gave us something that works nice, so take the square root. We aren't, our hypotenuse will never be negative, so this is good. And this will be 17, right? So all we have to do, this is a bit weird, but all we have to do to get UV, or UW in this case, right, is we'll say, let me do this. So UW, and U, I guess technically also has an arrow, or maybe W doesn't need it, but okay, if we put the arrow just on the U, that's fine. UW is going to be my vector W divided by this number. So what that means is I take each piece of my vector, so -8 and 15, and I just divide it by 17. That's it. That's all we do. Right? Yeah, simple enough, right? But in order to check, so it says, notice here, it says verify that it's a unit vector. Okay, so I is 1, 0, like the letter I represents the vector 1, 0, and maybe I should go, no, we'll do this. I is 1, 0, the vector, and it's this vector right here. J is 0, 1, and it's this vector right here. So the unit vector, these are the unit vectors, right? In the direction of the positive X and Y axis. So you could have negative I, negative J, right? And basically they form, if we had negative I and then negative J, basically what's going on here is they're forming the unit circle. And that's also why these are all related. That's also why they're called unit vectors. Unit circle, unit vectors, we're all, something has to do with ones, like in 0, like it's connecting everything, right, for us. So these are our unit vectors, and the representation, the way that we write a regular vector, like V equals AB, in terms of the unit vectors is like this. So let's real quick, if we wanted to write, I'll give like a mini example maybe. If we took this W, and I'm gonna just do this, in terms of I and J, W, the vector W would equal -8I, and typically that's written as a vector, plus 15J, right? Because technically, okay, if we did this, if you plug in, look at I and J, if you plug these in, and then you do that weird scalar type multiplication and stuff we did up here, you end up getting -8, 15 as a vector, right? You get W, exactly what W is. So there's just multiple ways, and sometimes it's easier to basically just write it as the coefficients and ignore the vector piece. And so we write this, we think we're clever, but we write this in terms of I and J vectors, and it's kind of like X and Y component vectors, right? But it looks like an equation, and so math people probably just prefer that. I mean, that's probably how I am, so I shouldn't really knock it, but yeah. And keep in mind something that's super weird here. This is not the imaginary I. It's just a regular, it's just a regular letter or like variable. So it's not the imaginary unit I. It's just our vector I.
So the another quick question.
Yeah.
Or something that was mentioned in the chapter was that the magnitude is, if you calculate the magnitude of the unit vector of W, it should equal 1, right?
Exactly. So that is where, if we wanted to verify this, which I'm just going to be lazy because I didn't want to write it, but that is exactly true, right? So if we did the magnitude of UW, this is a unit vector, it should equal 1. If it equals 1, then check, we're verified, we're good. If it doesn't, we've got, we did something wrong. So basically, you would just take, to get this magnitude, you would basically take the square root of -8 over 17 squared plus 15 over 17 squared, right? So hopefully, I mean, okay, if you do all this, this should work out nicely, because you'll get 8 squared, 64, 15 squared, 225. You'll add those up. This will end up being the square root of 289 over 289, right? And then that's how you get 1. And that is why we divide. We're basically, so if you think about when we rationalize the denominator, we're kind of taking this vector W when we divide by the magnitude to make it a unit vector. And we're kind of, what it's called is normalizing. We are normalizing the vector to a unit vector. It looks maybe different or bad, but it is typically good. If that makes sense.
Like, why do you have to do that? How does that?
So, okay. So I've had an answer to this in the past. And at the moment, I'm not remembering. Like, I know there's a reason for it and why it's like helpful or useful. But at this very moment, I am thinking, why do we do this ever? I'm thinking the same thing. But there is a reason, and maybe we'll get to it in either later today or hopefully Thursday. But yeah, and the textbook might explain it as well if you are reading that. But yeah, right now,
something very important about it.
Yeah, I'm sure. And it could be. So here's where it could be a calculus reason. It could be that in calculus that's more useful, but in pre-calculus, and again, personally, I think pre-calculus is harder than calculus, and it's because you're learning all of these things, and it's kind of the reasons why everything, and then in calculus, you get all the shortcuts, and you can be like, I just do this shortcut, cool. But the reason for all of that is embedded in pre-calculus, at least in my opinion. I mean, part of it is probably fully true, but I also just really believe this.
Yeah, that's cool.
Yeah. Okay. Fingers crossed, Veronica. Yeah, that calculus is way better. I mean, I'm not okay. I shouldn't promise that, but I will say, like, even Paula McKenna. Even for like, I am a math person through and through my whole career. And when I was in high school and college, like I struggled with pre-calc really badly. Like, I mean, C's got degrees in terms of, for me, like I did not get it. It was very difficult. I also didn't work very hard. So we can't really, but then in calculus, everything made more sense. It was still probably hard, but everything made sense. It was so clear, or it was so much easier, at least I thought. So I'm hoping that is the case for you guys too. Even those of you doing well in pre-calc, you really should get calculus, I think. I think it's like, for whatever reason, it's easier. But anyways. So number 9 is asking us to write this vector in terms of I and J. This is not the quote, right? This is just translating it's kind of like the mini example I did above. So this would just be, this is the I and this is the J. So you would just write -12I with a little, my I is kind of gross, but okay. -12I, the vector, -30J. You could write plus -30, but that's weird. We don't do that. So this is that vector in terms of I and J. And I will say the I and J thing is way nicer to me than writing vectors like this when you're solving things and later. And I wonder if when we normalize or get the unit vector, I just wonder if that's also related, like, to just having I and J or the unit circle or something like this, right? I'm sure it all comes back, and we'll find it. So now we want to relate this component form that we've learned, and then the direction and magnitude of a vector, right? So if I have this, they're showing this graph here, and I'm just going to maybe redraw the triangle for myself. So if I have, this is theta, I have this right angle, right? So pretend this is here. This distance is A or X, right? But this distance is B or Y. And then this distance, the hypotenuse, is the norm of V, norm, the magnitude. Norm is kind of the same thing. I don't know if that's used in like physics or something. Now we have some, and you can picture this, picture it like this, but I just redrew it over here because I was drawing the triangle separately. And then I wanted to show you that it's also related here to this comes from the Pythagorean theorem. So again, that never really goes away, right? Trig went away a little bit for a minute here, but it's going to come back. So don't you worry. So then what we have here is, well, and the reason you'll see for these, so before we take a look at these equations, we can see that, this weird color, we can see that if I had cosine theta is like, I'm thinking SOHCAHTOA, maybe I should start with sine, but if I have cosine theta, it's the adjacent side, which is A, over the norm of V, right? Which means that I could, well, all right, let's now, sine of theta would be opposite over the norm of V, which is the hypotenuse, right? But that means if I wanted to solve for A or B, and I knew the magnitude, and maybe the angle even, right, I don't know, then you could just multiply both sides by the norm of V, or I'm sorry, the magnitude. I should try to keep saying it right, but hopefully you're following. And when we multiply that and cancel it over here, we get a formula or an equation just for A and B using sine and cosine, but right, but yeah, that's fine. So now we come to these formulas. Okay, magnitude of V is Pythagorean theorem, and it comes from the fact that we can draw vectors like this triangle in this photo here, right? And we can form this 90-degree angle and use Pythagorean theorem because it's very handy. And then we can also use this tangent of theta equation as long as A is not 0. So, I mean, granted, it typically shouldn't be, but as long as it's not, we can say tangent of theta, if you need to get theta or anything else, is B over A. So if you know, and these are both related to the magnitude and the direction of V, if you know any of either A, B, or theta. And then the next piece we see here is what I just wrote. I mean, what we saw like here and here, right? A is the magnitude of V times cosine theta, and B is the magnitude of V times sine theta. And these are the components of the vector. So these will represent like the components, as in components that go inside these weird brackets, right? Where it's A comma B. But the magnitude and direction, so the magnitude is this. This is a scalar, the yellow highlighted, so maybe I'll match these. That's the magnitude. And the direction is the like tangent theta or equals B over A. That would give you the direction, like the angle. Because if it tells you, oh, it's 40 degrees, well, then it's in the first quadrant. If it's 120 degrees, it's in that second quadrant, etc. Right? If it's negative 12 degrees, it's in the fourth quadrant. So it should tell you where that is. And then the components of V are A and B. So now that we have all these handy dandy equations, which again, I actually don't, I want to say on the next exam, you might get a little cheat sheet, but I have to look into it and I don't truly remember. So I apologize for that. But I think we might allow that because there are a lot of just little equations here that, so if they're not written right on the test, I wouldn't mind, whether you printed it or I just put it, like posted it with the exam if you refer to that. Okay, so let's see. If I want to write vector V in this form with I and J, AI plus BJ, and then V has magnitude 10, and theta, the direction angle, is 3 pi over 4. So 3 pi over 4 tells me, what is it over here, right? Okay, I should have drawn that better because we know it's like exactly in the middle, but okay, right? 3 pi over 4. It's over there. So that's actually going to tell me that A, like this is, it will be negative A and B will be positive, right? So that kind of is useful, or it is useful, right? Okay, so now if we want to solve this, we can say, use our equation. So first I'll do A and B. So I can say A is going to equal the magnitude of B times cosine theta, and B is the magnitude of B times sine theta. So we can plug these in. So 10 cosine 3 pi over 4 and 10 sine 3 pi over 4. And we can do, I mean, I'm doing this in my head because it's a nice angle. If they give you an angle, you know, maybe that's not so nice. You can definitely use a calculator. Or even for this, I mean, if it's just the homework, right? But remember, this point is negative root 4 over 2, negative root 2. Oh, wait, no, this is negative, this is positive. Oops. And then it's root 2 over 2, right? So, my bad, I should. Okay. So here now we have 10 times the cosine is negative root 2 over 2, and the sine is positive root 2 over 2. And so we have negative 5 square root 2 and 5 square root 2. And so I'm not done. What did they ask us? They asked us to get V in this form with the given information, right? And so if I give V in this form, I would say this is negative 5 square root 2 I plus 5 square root 2 J. Right? And then 11 says, the question's asking, find the magnitude and direction angle. And it's telling us between 0 and 360. Because remember, if the angle is, you know, okay, if the angle is here, it could be this little angle. It could go around and around again. It could be, you know, negative. Like who the heck knows, right? So they're telling us, find the angle between 0 and 360. Use that. And notice how it could equal 0, but it cannot equal 360. So just good to know. For S, so now they gave us S equals negative 7I plus 3J. They gave us this piece that we just found in the previous answer. And notice how if we have to round, that means it's not going to be a nice angle like 3 pi over 4. So we'll have to round, and we can do degrees then if it's, I mean, up to you. You can do radians as well, but I would probably do degrees. So we want to round that to no decimal. So we are given, we have some angle, and we are given S, the vector S, and it's equal to this, but it's also equal to negative 7 comma 3 in these block, like this special type of pointy bracket, right? And so when you think of this, okay, this is my A and this is my B. So looking at the equations, I think we're going to use the first two because we're given A and B. We don't have to solve for A and B. So in this case, I'm going to start by saying, okay, tangent theta is B over A, which should be 3 over negative 7. Right? So tangent of theta is negative 3/7, which means that we want to find inverse. So, okay, let me erase this because we'll have to think about this. Let's see. But we also know, so before I kind of fully solve for theta, we also know that A is negative and B is positive. So that means the triangle, it's somewhere over here, right? Where this is negative 7 and this is positive 3, right? So it's somewhere over here. This is our triangle. And that means that our theta is in this, like this direction. It's not going to be, so if we get a negative value, it just means we have to like subtract that would be this little guy, and we'd have to just subtract it from 180 or something like that, or add it to 180. Okay, so let's take a look. So if I solve this, I get, well, I'm going to take inverse tangent of both sides. So I'll get theta is equal to the inverse tangent of -3/7, right? And this is about, if you do this in degrees, I get about -23.2 degrees. And so again, that would tell me, if this was the case, -23.2, okay, would be like somewhere in here, right? That would tell me this vector is here, but that would tell me that this was 7 and this was -3, right? It would tell me that this piece was 7 and -3, but we were told the opposite. So that just means we have to, the angle should be here. And what we found is this little angle here, but we want the bigger one. So we're going to subtract, we're going to do 180 minus 23.2, because this means that the theta, okay, maybe I'll do an arrow. So this means that the theta in there is 23.2 degrees. But again, we are interested in from the theta, the bigger theta from starting from the x-axis, okay, not the reference angle. So we are going to calculate this by saying, okay, so our theta, okay, so maybe I don't know how to write that, but maybe our theta, the one we want. So if this is theta, but this is here, is going to be 180 degrees minus 23.2 degrees, which gives us 156.8 degrees. And so this is our theta, the theta that we wanted to find, right? The direction angle. Well, you also, okay, so another way to know this is we got -23.2. They asked us for this. So I was kind of over analyzing it there, but they asked us for 0 to 360. What would this be? And so you just have to figure out where this is going to go and how to get that, right?
Since you can I ask you a question, since we're using, since you have to, in this case, use the inverse of tangent, and isn't the inverse of tangent restricted to like 0 and like pi?
Yeah, so it is. So it typically, I think, is it restricted to 0 to pi? Yeah, 0 to pi or -pi/2. It's 0 to pi probably, right?
That's what I think it is. I mean,
yeah, but in the calculator, so yeah, but in your calculator, at least that's what it gave me. If your calculator gave you 156.8, that's great, but mine did not. So, but like you said,
I got -23.
Yeah, so that, but that tells you that typically that's going to tell you just have to subtract from 180, or take that from 180.
Okay.
So yeah. Now, sometimes it might be set up where if it's in the first quadrant, for example, like you'll just get the right angle right away, which that's always really nice. And then to get our magnitude, we still didn't get that, right? And our magnitude is just this like double bar, the norm, or the magnitude of S, is just the square root of each of our components squared, right? So -7 squared plus 3 squared, right? So I get the square root of 49 plus 9, so we got 56 maybe. And so, oh wait, 49, that is not right. 49 plus 9 should be 58, right? At least I think. 40, I did it right, 49 and 9, yeah, this should be 58. So the square root of 58, and this you could leave it like this. However, it does say to round, and so I'm going to also round this norm. So we'd say the square root of 58 is approximately like 7.6. Okay, so there's our magnitude and direction. direction angle, I guess. We aren't saying, but technically that angle goes what? North, what? East, west,
Like,
west.
yeah.
Yeah, I'm trying to figure that out. Okay. Now, this next question is more similar back to number 10, where we use those formulas. So it says a baseball is thrown, oh, wait. Okay. A baseball is thrown with a speed of 65 miles per hour and an angle of 12 degrees from the horizontal. Write the velocity vector v at the time of release in terms of I and j, and round to the nearest tenth of mile per hour. Okay. So what I see here is, or what I'm hearing here, right? Horizontal is here. We're like going up 12 degrees, right? At an angle. And then and this is our vector. And we're assuming it's the magnitude is 65 miles per hour, right? Is that what they said? At a speed, or yeah, that's the speed. So if this is our vector v, then they gave us the magnitude is 65 miles per hour. And then they gave us the angle is 12 degrees, right? So we want to calculate in terms of I and j, we want to calculate a and b, right? And then just write our vector. So to do that, I'm going to use those formulas. A is the magnitude times cosine theta, and b is the magnitude times sine theta. And that's going to be 65 cosine of 12 degrees. Now make sure your calculator is in degree mode here. Oops, this should be sine. 12 degrees. And it says to round to the nearest tenth, so we can do that. So that would be for cosine, it's 63.6, and for sine, which is b, it's 13.5, right? And so with these, we can say, okay, the vector v is going to equal 63.6 I plus 13.5 j, right? And this is the velocity vector v at the time of release, written in terms of I and j. So this, because they gave us magnitude and theta. Oh, and I think there's a typo here, but we'll see. Or maybe I put it on the next. No, yeah, there's totally a typo. So we'll figure this out. So we're probably, and I'm thinking the bearings. So as you can tell, we're gonna do number 13, and then maybe I'll explain where the typo is that I left out, but we're not gonna get to bearings today. I will have to make sure that we will have time, because I don't know if this is related to your homework. Oh, I guess your homework's due over next week, so this is good. So if you do see problems in your homework that are related to bearings before Thursday, I mean, you can save them for after Thursday if you aren't sure. But we will take care of this, and I'll do my best to finish 8.5 as well. I'll take a look at it tonight and make sure I can get there. If not, maybe I'll pick some things to like skip over or just provide notes or something like that. But we will do number 13. So let's check this out. When's the next test? Joseph just asked. 2 weeks, 3 weeks. I'm not. Oh, November 10th. Oh shoot, that's like, is that next week?
Yes.
Oh wow. Okay. Sorry, time has escaped me. It is next Thursday. Okay, so I will for sure finish 8.5, 8.4. I'll wrap up Thursday and I'll finish 8.5, and then I'll provide the review for you Thursday night. And then next Tuesday we will just review. I'll answer. Maybe if I skip any questions, maybe that's what I can do next Tuesday as well. And then we can review and you'll have your test. Yeah, wow. I'm sorry, I did not realize that. You're like a week ahead of my other class in terms of testing. So I thought we just had way more time because their test is like 2 or 3 weeks away. So, okay.
Can I just mention that
yeah.
that for that last test that I did those practice problems that were like out of the book, that was, I don't know if you're going to give that to us again.
I will. I'll give you both that and another just review. The book prompts were really helpful.
Yeah, that's what I was going to say.
Okay, good. So I will give you that again. Yeah, for sure.
Thank you.
And I'll provide it this Thursday night. I'll check Blackboard after class tonight and make sure that I'm going to post it by Thursday. So you'll have the whole weekend and then all next week as well. Yeah.
Thank you.
Yeah. Okay. So number 13, the forces. So there's two more types of questions that we're going to look at. We'll look at one tonight and one on Thursday, but use vectors and applications. That's what these are. So one of them is the bearing, right? Which we'll do next time, but this one is forces. So the forces in units of pounds, like F1 is 10I minus 3J, F2 is negative 2I plus J, and F3 is this 11I. They act on an object. If we want to find this resultant force, which we're calling R, this just means we just add all forces together, right? And now you know how to do this. So what this means is you are adding the I's with the I's. Maybe I'll do this. The I's with the I's, the J's with the J's. That is what you are doing. You are not combining the two. You are just adding these. So let's take a look. So if you have, technically you just want F1 plus F2 plus F3. This is going to be R. And these are all technically vectors because they're bolded, right? So this is going to equal, so watch what I do here. 10 minus 2 plus 11I, and then plus negative 3 plus 1J. I literally took the coefficients of I and J, and we are just adding these together. Don't overthink it, right? So this is going to be 10 minus 2 is 8, plus 11 is what, 19I, and then negative 3 plus 1 is negative 2, so minus 2J. This is the resultant force, right? That is it. And then it says find the magnitude of that force to the nearest 10. Well, magnitude of R is just the square root of I and J, of the I coefficient and the J coefficient squared. So it's the square root of 19 squared plus negative 2 squared. And this is, oh boy, I should know 19 squared. Let's see, 19 squared, 361 and 4, so 365. Okay, so we get a decimal here. So I should have probably computed this before, but I just did it, so it's fine. So this is 19.1, and it's in units of pounds, so technically it's pounds. So the magnitude of whatever this force is in this problem of the acting on an object, it's 19.1 pounds. If it's your dog jumping on you, I don't know, maybe it weighs 19, or like weight double that, like mine. Okay, now let me just go through the typo real quick, or the part we're missing. So technically I wanted another problem here. We'll call it 14. And I think this is even 15. Yeah, see, this was 15. So 14, it talks about this current and a swimmer, right? So if we're swimming at one point, if someone, a swimmer, is swimming at 1.6 miles per hour in still water, this is again one of those like imaginary, or maybe it's a lake or something, something calm. But suppose the current is 0.4 miles per hour due east, then we can ask ourselves at what angle theta should the swimmer swim to reach point B in this picture. So again, I meant to have this in here, but here's the, and because of that slight current going this way, right, the swimmer technically should not swim straight towards B because they'll be pushed and then they'll end up to the right. So technically they should swim slightly to the left. And if we knew that angle, we could, that's what we're calculating here. So I won't maybe finish this or maybe I will. Let me so for those of you that do have to go, I will take a few minutes to finish this problem. But those of you that need to go, you can, I don't think I picked a question of the day for today. Shoot. Have I asked you what your favorite age so far is? Have I asked everyone that or no? Maybe I did.
No, I don't think so.
Maybe I didn't. Yeah. Go ahead. Favorite age.
Favorite age, like in your life?
Like in your life, yeah. Or if you think it's going to be a future age,
or the age you would like to be.
Yeah, well, yeah, I lie about that, so we won't get there. But yeah, maybe it was, maybe it was 40, maybe it was 12. I don't know. Yeah, maybe it's going to be 65. Maybe who knows?
When you retire.
Yeah, right. I mean, if you ask some people, that's what they say. So there's a question, but let me just finish this problem and I will post these notes and then we'll finish. I'm going to write that we're ending here on today and we'll start here on whatever the heck, Thursday. But just to see this, this 1.6 miles per hour represents a unit vector or vector. We're writing this as V sub B. We'll write this as this vector. Yeah, and some people, I love it. I love everything. Post death, that's a little bit dark. I think. Maybe you're a little stuck on Halloween. But I hope that's not maybe totally true. But so if I call VC as the current, right, the vector here is 0.4 and then 0, because it's just 0.4 due east. So it's not anything north or south. And then VB is the vector, or the velocity in the still water. And this is magnitude cosine theta, magnitude sine theta, right? So this is the current velocity of current. This is the velocity of in still water. In still water. And then if we want to figure out what is the true velocity, so this would be our true velocity, we would just add these up, right? Because the current is pushing you back a little bit. And so we can figure this out just by adding that if we wanted to, right? And so V is going to be 0 and B, but in this case, we don't know B, right? It's not a question. We don't know. This is a question mark. B, what is this? So we can, in order to find this, we can use, I'm going to box the X. So can use the X components to write an equation. And this, I'm just guessing that this will help you on homework. The tests are not this complicated, but we can use this to write an equation. And that equation would be something like 0.4 plus 1.6 cosine theta has to equal. So we want V to equal this. So it has to equal 0, right? Then we would get 0 plus 1.6 sine theta plus B. It has to equal B, but we don't know. Once we can get theta, then we can get B, if that makes sense. So here we get cosine theta equals negative 0.4 over 1.6. Okay, whatever that is. That's negative 0.25, I think. And then we would take the inverse cosine of negative -0.25. And this would be our theta. And it's about, I think, 104.5 degrees. So, and that makes sense in this picture, right? If this is like 104.5 degrees, you're swimming slightly past that 90 degrees north. You're swimming slightly the other way, opposite the current, so that at your speed that you swim, or this swimmer, if they swim this direction, the current will slightly push them. And by the time they end up at B, or at that, distance away, they'll be at B and they won't be off, if that's like the shore, or if that's a diving boat or whatever, a dock, a boat that they're swimming to, or whatever it is, right? So that's kind of the point there. So now that we found theta, we basically can write an equation, like I said, that takes all of the y components, and we would say 0 plus 1.6 sine theta has to equal b. And so 1.6 sine of 104.5 degrees has to equal b. And I don't even think I calculated this. Yeah, it's obviously been a difficult day here, but this is what we will get. So let's see, 1.6 sine 105. Let's see. Why is this not working? It keeps giving me radians. So let's see. Okay, so 1 point, B is about 1.55, but we'll say 1 point. Oh, that doesn't seem right. I got 1.549, but what was B again? Oh, little b is this distance. Okay, so this makes sense. So the distance should be very, very close to 1.6. And really, we shouldn't be rounding this. But this distance is what you would actually be swimming. And then the current's kind of pushing you towards the end. So you're not missing very much. And okay, my bad. We didn't even need to find B technically. I had just asked at what angle should the swimmer swim to reach point B. So it makes sense that it's still about 1.6, whatever. I don't know if it's miles or what. I guess miles. But so we found our angle, and it was this 104.5. Okay, so I'm very sorry for going over here, but hopefully, so I'm going to save this before I forget, because I'm totally going to mess that up. Save 2 files. Yeah, let's do that.